All right, welcome to the episode number 4. Again, let's go over the announcements first. Okay, let's see, where are the announcements? Right here. Okay, so for today, lecture number 4, episode 4 is online here. Oh, by the way, I actually mentioned a couple of times the reading brief about the core technical contents. I made them into short video clips so that if you are a little bit confused about a particular part, you can always click back there and then take a closer look or watch it again. So I think it's accessible from the course page, and there's a link called video right here, video. Just click into it. Oh, you see. For episode 2, we spent quite a bit of time going through the Slack workspace to make sure that you guys know how to operate it. So in that lecture, we only went through terminology, and then I talked about chapter 1, the flow of chapter 1. So it's kind of the overview of the entire chapter. And then we played the video giving you a nutshell of what internet is like, right? So this coarse grained picture of the internet. And I displayed pretty much all the components, the physical components of the figure. And just 2 days ago, Tuesday, so that lecture is then substantial, right? We went through quite a few topics. For example, you see the internet is an internet of network of networks, service view as opposed to the physical view. And then here in the protocol part, the description is relatively short. I just show you a couple examples, right? One for human communication, the other for computer-computer communication. So it will still be a little bit vague if we just talk about what's described in the textbook and the examples. So for that, to make it more concrete, you get the better sense. We had a quiz, remember? So what you guys were doing there, solving quiz 2, is to define the protocol of greeting. And if you went through other students' quiz 2 solutions, you might see that, many of you consider all sorts of situations, right? Cultural background, where we are, age, social status, gender, and how close you are to this, friend of yours, things like that. Some of you say that you observe, but in case the situation is not exactly clear, I think some of the team actually propose the safest way as the default, right? If your sensory of this person you need to greet with is not good, or if you don't have time to observe, then you go with the most commonly used greeting form. So you kind of devised a protocol yourself. Every time you see someone and you need to greet someone, then it's very clear now what protocol means to you. It's just a set of rules how you exchange, with somebody else. Similarly, a computer protocol, a network protocol, is for computers in the internet to try to interact. So there are a lot more, and I'll be adding more for today, episode number 4. Excuse me. Okay, and the class is in a healthy size, perfect size, in fact, 42 students. According to the department, we do have 38 seats here, but that's maximum, and that's kind of, a little bit crowded in terms of airflow, because we only have one one entrance, one exit. So it's good still that we have some vacancy here, there, and some of you guys tuning from the internet. But good news is that therefore, those who prefer to attend physically, you guys will definitely find seats here in the classroom. All right. So these two are, again, just to tell a little bit more about using Slack. For today's quiz number 3, yeah, the channel are probably not visible from your channel list. Because when you join Slack Workspace, you're automatically added to the channels that are already being created. So Polly and Caleb are also creating channels, okay, as the lectures progresses. So Polly actually created quiz number 3 just Tuesday. The W2 quiz 3 channel. So to many of you, right, this is not on your channel list. In order to add that into your channel list so that it's visible to you, so there'll be new channels being created, right, as quizzes being added. So to add a new channel is rest the cursor to the channels row on the channel list. So where is the channels row? Okay, here. And once you rest your cursor here, you see the plus sign showing. Click, and you see the browse channels. If you click, you see all the channels available from the workspace. Some of you automatically joined already, but some of these channels you automatically joined already, but some of these channels are new, and you'll have to kind of join. And of course, if you get tired of that particular channel, you can also leave a channel, all right? Okay, so guys, rest here on W2 Quiz 3 and hit join here. Oh, I see 9 members joining already. So that's how you add a channel. And if you go there, okay, you see quiz number 3 is already posted. And 又得 team number 8, they act really fast. Even before we talked about this part of the lecture, they have already, okay, yeah, so Polly said that I've got to give them a pui. So now there are 4 pui. Oh, okay, more coming in. Yeah, so the way we're using these emojis, very interesting. I like, Thomas cars or Tommy cars. So sorry, I should not be saying too much there. Then you know I'm really a geek. Okay, sorry. Let's go back. Oh, occasionally I post fun things here. Right? So Holly posted reflecting how we are using emojis in class. Okay, so it reminded me of American drama or comedy, sitcom, American sitcom. Maybe I can play it a little bit here. Some of you gave me alligators and sunglasses. So I'm saying, hey, back to you. Okay, and to you. All right, so that was how you add a channel. And Polly just inventoried the Slack workspace user account. And I think I kind of clean the user accounts that are created. So some students came to try to find out how the class is organized, the scope, and then they probably got into the wait list and got into some of the courses they would like to take more. So they are no longer with us, which is good. And so I kind of deactivate those user accounts. So in case I accidentally deactivate any of your account, so if I accidentally, please let me know so I can reactivate them. 6 of you do still have 2 accounts remaining, so we would like to deactivate one of them so that we can track the participation a little bit easier. Okay, so please. Just let me know. I think one of you did that already. I forgot who. I think it's Zhang Jingxiang. Okay, thank you. Jingxiang just texted me, yeah, saying that yeah there was an account created earlier. He just signed out, not knowing exactly whether the account is activated or still activated or already deactivated. All right, good. So that's all I want to say, and then we can now go back to the lecture. Well, let me go back here. So this was what we were talking about, right? At the end, Tuesday. Much of the Tuesday is what? About the access net technologies. Recall. ADSL. Mm-hmm. What else? Ethernet, right? Wireless access. And we talk about in home nowadays. We use all these access technologies in combinations because nowadays a home network is somewhat complicated. Can be as complicated as a small scale institutional network. And we continue and try to wrap up the access network because each of these access net technology is defined as a protocol, but there's also a physical media, right? For ADSL, for cable modem, for FTTH, there are physical links, physical medias being used for it. And for wireless, it's a different kind of media. So let's take a closer look at how they work.
Here we're going to switch gear a little bit, but still about access network technologies. And so far, if you paid attention, each of these access net technologies operates on some sort of mechanism or protocols. They also operate with assumption on there's a companion physical media. This is important, just like the protocols are important to achieve a certain expected performance, typically achieving a really high bandwidth. Okay. Now, so let's go over these physical medias that work side by side with each of these access technologies. Now first, let's define some terms. Bit. These bits are propagated between the transmitter and the receiver. And between the transmitter and the receiver, whatever the media is called a physical link. And these links can be wired. There's a special term called guided media for it. If it's wireless link, then it's unguided media, meaning that the signal might just go propagating omnidirectional everywhere. Okay. As opposed to guided media, there's usually a copper wire or an optic fiber that the signal kind of just follow and being guided to travel through the physical media. Now, there are four kinds of physical medias we'll be talking about. First is twisted pair, and this is one of the commonly used cable for Ethernet. Cat5, this is very old for Ethernet that's 10 years ago. Nowadays, I think we're still using a lot of Cat5 cables, which supports up to 100 megabits per second and might be reasonably okay for 1 gigabit Ethernet. But if you purchase a 10 gigabits per second switch for intensive use, make sure you get these cables. Cat6, particularly 6A. This will allow you to have physical transmission bandwidth up to 10 gigabits per second. Just, by the way, it doesn't make sense to buy a really high-speed switch and the cable limits the speed. Okay. Next in line is coaxial cable. And this picture shows pretty much the structure of such a coaxial cable. What I meant by coaxial is that they have two layers, concentric, and these two layers of coppers allow you to send signals. And because having two layers, it kind of allow the demodulators to easily cancel out the noises. And so data goes bidirectional on such a cable. A very primitive form of this coaxial cable was used by the legacy Ethernet. Yeah, by baseband, it meant that the bandwidth is really, really small, very low rate transmission, and it doesn't exist anymore. But then cable network picks it up a bit, intends it somehow so that they can send multiple video programs over it, allowing multiple channels on the cable. And the cable exactly used by the cable network is HFC, the hybrid fiber copper cable. Oops. And the third is the fiber cable. Okay, so this is entirely glass-based fiber, and the bits are being sent as pulses. Okay, like that. It works in a very high speed. You can go up to hundreds of gigabits per second. These high-speed fibers are oftentimes used by also the internet backbone, where lots of data are being exchanged. It's also used by the data centers, where there are always high-volume data that needs to be stored or retrieved. These fibers, as we heard, FTTH, some of them, slightly lower end, is used for residential access as well. And they are very high speed, partly because it's very low error rate, because they are more resilient to white noises, background EM noises. The last media is the radio link. This one is very special. It is in fact the one that's used by all wireless and network access technologies. So what's listed here are just a few examples. Terrestrial microwave, operating at about 45 megabits per second maximum. Wi-Fi, well, depending on the version, could be lower, 10 megabits per second, or half of 100 megabits per second. Wider area wireless access, 4G, for example, goes up to a few megabits per second. 5G is now tens of megabits per second, okay, with the potential going higher than 100 megabits per second. And satellite radio, yeah, the bandwidth range spans wider with satellite, probably because of where the satellite is exactly and the technologies being implemented on that satellite. It can go from kilobits per second to 45 megabits per second. But one common feature is this. For satellite links, end-to-end delay will always be much longer than all these other wireless link access. Now, as to exactly how long the end-to-end delay is, it really depends on where the satellite is. For geosynchronous satellites, which sit higher above above Earth, the delay will get longer. The low altitude ones being lower, then shorter end-to-end delay. So, radio links, very special. Essentially, we are sending bits through these electromagnetic waves. There are no physical wires, so it's called unguided media. Data can go bidirectional, well, in fact, all directional, which is a good and a bad thing. If you think about the propagation of these electromagnetic waves, it can be influenced by environmental effects. Having objects around, the objects can obstruct further propagation of the electromagnetic waves. And some objects might reflect, these waves as well, And the waves can be interfering with each other, coming from different sources, or even coming from the same radio source. It's called the multipass effect. So physical media, radio, it's very convenient, but you see the challenge of transmitting signals through these magnetic waves. You see also generally the wireless links, the maximum capacity usually lower than the guided media's capacity.
Alright, so in this video, it features the other TA, Honey Huang. So excuse the cat meowing. And by that, we finish AccessNet, the edge of the internet. Okay, we are now moving into the core. Core is actually the interesting part and the hard part. Oops.
As access network is concluded, let's move on to the next component, the network core, which is a mesh of interconnected routers, as I'm trying to highlight here in red color. So you see a bunch of routers very well connected to each other. By well connected, let's see, if you count how many connections this router has to the rest of the internet. 1 here, 2, 3, and 4. 4 connections. Look at this one. How many connections? 1, 2, 3. Look at this one. It's an edge router, all right, but how many connections it has to the rest of the internet? 1, 2, and here, 3, 4. But if you look at a end system, such as this one here, how many connections it has to the internet? Just one here, through the Wi-Fi AP. Look at this PC here, only one. One very clear distinction between these routers to all these end systems is exactly in the connectivity, the number of connections they have to the rest of the internet. For routers, very oftentimes you see more than 2, including 2 connections. For end systems, just 1. And the reason that the routers oftentimes have more connections is because their role are just to transfer data. So it takes us to this very fundamental question. How do we transfer data in such a well-connected mesh network? In general network, communication network design, very general communication network design, there are 2 major mechanisms. First, circuit switching. Second, packet switching. Idea is quite straightforward. In circuit switching, from the source to the destination, let's build a dedicated circuit, and this circuit is going to be reserved through the entire time of communication, so we could just dump data in. And the performance is guaranteed. And this is the mechanism used by the traditional telephone network. The other technique, packet switching. Instead of allocating resource, creating a dedicated circuit, let's just use the entire link capacity. And let's send data out, no matter what. But we cut the data such that it's sent one chunk at a time. And to call such a chunk of data, we have this term called packet. All right, so it's almost like a package, but packet means also a little package. Okay, so we send data in smaller chunks, but use the entire link capacity. And to tell you ahead of time, internet or the data network is taking this packet switching approach.
All right. So that's the main point. Let's talk a little bit more about circuit switching. Okay, so make sure that you get the idea.
All right, now let me elaborate circuit switching a little bit more. This is the familiar network. But this time we see on the network there are 2 circuits. The red circuit connects this end to this other end. Similarly for the blue end. And to establish such a red circuit, which is also called a call sometimes, and the time it takes to set up such a call or such a circuit is also called the call setup time. Okay. And the reason that I need to mention that term is because that takes time, because resource reservation is required going from one end to another, which means this is the first link on the circuit. We need to reserve a certain amount of bandwidth to guarantee that data gets transmitted without any loss or delay. So you reserve link bandwidth for the call. Data is going to go through a switch. This is the first switch. On the switch, memory, CPU, buffer space will also need to be allocated and reserved. So that is what I meant by switch capacity here, to guarantee that the packet will not experience delay and not experiencing any loss. Similarly, for the second hop, for the third hop, fourth hop, fifth, sixth, seventh, and eighth. When all 8 hop link bandwidth switch capacity reservations are done, then you build a circuit. But then you see, as Polly was describing, this circuit here, resources are all dedicated. When data are being passed through, no delay, no loss. Really nice. And we call that circuit-like performance. That implies delay and no loss are guaranteed. Low delay, no loss, guaranteed. Similarly, for the blue circuit, and this is really nice because zoom into this segment. This segment here shared by the blue circuit and the red circuit. The two of them, although packet or data will be going through, but these data will not interfere with each other, not incurring delays to each other, and not collide to each other. No packet drops. These days, where we do online meetings a lot, having live YouTube channels a lot, we'd really like to have this circuit-like performance. This way, we don't have to worry that internet is going to go bad and the live stream is going to break at some point. Nice. Because for certain applications, we do need this type of quality of service. But, you see, establishing the red circuit, we need 8 hops, and each hop takes some time to reserve resource. So there's quite a bit of call setup time involved. This is the downside of circuit switching. Another downside is this. The way we are allocating or reserving resources over the entire path from the two ends of data communication is more. We divide the link bandwidth into smaller pieces. We divide the switch capacity also into smaller pieces. And once we do that, we allocate individual pieces or combinations of pieces to an individual circuit or individual call. But once you do that, if there are no data being sent between the two ends, that piece of resource will then be idle. If you think about it, in a way, it's a waste of resource. If the two of them ask for resource and a call established, but they are there sitting doing nothing. So not very good utilization of resource. So this is the second disadvantage of doing circuit switching. Now, speaking on dividing link capacity into pieces, there are multiple ways of doing that. First one is called frequency division, the other time division. This is the second time we see the term FDM. Where did we see this? Yeah, cable modem. We divide cable modem capacity. We divide the cable network link capacity into what? Pieces by the frequency band. This is a very different flavor. Okay, it's dividing the link by the time. Let me illustrate. The example on the top is doing FDM. where we divide the entire frequency band there to 4 users in equal division. So full frequency band, 1/4 to the blue user, 1/4 to the green user, to the yellow user, and the pink user. TDM works this way. Instead of dividing the frequency dimension, let's divide, okay, in the time dimension. So with these time slots, we allocate the time slots in a rotating fashion to the 4 users like this. Blue, green, yellow, pink, blue, green, yellow, pink. Yeah, it's rhythmic. That is exactly how TDM works. With a good rhythm, with well-synchronized time, the 4 users can send data one after another. Very orderly. If we have more than 4 users, how do we do that? You see, we could further refine the division into, for example, A parts. That way we can accommodate how many users? A users. Similarly for TDM.
All right. Get the basic idea of circuit switching.
To make sure you pick up circuit switching and how it works, let's see if we can work out this problem together. The question asked is, how long does it take to send a file, this big, from A to B over a circuit switch network? And in this network, all the links have the same capacity, 1.536 megabits per second. And each link is divided to 24 parts using TDM. And meaning that circuit between A and B only gets 1 slot. And the presumption is that to establish the end-to-end circuit between A and B, it takes this much time. Alright, so how long does it take entirely to send the whole file through? Let's work on it.
How long? Oops. Yeah. Sorry about that. Let's close these. Oops. There. So 1.536 megabits per second, but it's TDM into 24 parts, right? And between A and B, there's 1 circuit, and they are allocated just 1 slot. So that's only 1/24 of 1.536 megabits per second. So how much bandwidth they get between hosts and A and B? Let's see. If guys in YouTube, okay, so yes, cat faces, sure. You guys heard the cat meow, so I'll say, okay, good. Anyone? Calculators? I think it's 1.536 divided by 24, right? If my calculation is correct, I get something like 64K BPS. Is that right? Now, to send 640 bits over 64K BPS per second, how long does it take? 10 seconds, right? And plus the time to establish the circuit, so it's 10.5 seconds entirely. 0.5 to set up the circuit, and then 10 seconds to transmit the entire file. All right. Oops, sorry, wrong slide.
Now let's discuss more about packet switching. The mechanism is very simple, right? We simply cut the data into small packets. And as the link is available, pass it out. So each of these small packets will go on the link in full bandwidth. So if you consider L being the size of the packet length, and R being the link bandwidth or the link rate, the delay this being small, this being large. To send a packet, very small. This is one advantage. And then think about this. If you get two users, A and B, both are generating data and both are sending these packets out. If A is idle, not sending, and B comes up with data, B can send out, no problem, and in full link bandwidth. Similarly, if B is idle and A has data, no problem sending out. So there's no such a situation in circuit switching where B allocates all the resource, gets all the resource, and A having data to send, but A didn't get any resource as a result. B sitting idle, occupying all the resource, and yet A having lots of data wanting to send, not getting anything. Okay, so there's no idle waste there. Last is maybe a little bit less obvious. You see, bandwidth is used as full, so there's no need of dividing the link bandwidth into pieces. So the mechanism is also simple. Okay, being simple, there's no idle waste, and there's no call setup, resource reservation process required. Okay, packet switching can potentially be very efficient, especially for short data streams. Think about the resource reservation delay, the call setup time. It can be pretty long, and if you have very short data stream, then hey, the overhead relative to the entire need of sending data is high. So you can probably imagine now, data network, internet. At the beginning, we were just sending really short emails. It doesn't make a whole lot of sense just to send an email and you go all the way to set up a circuit. So another advantage of using packet switching is also because of the user demand. Now let's look at what's wrong with packet switching. First of all, we will have resource contention because there's no reservation mechanism. What if A and B, they all have a lot of data to send, so the resource demand is beyond the available resource. So we call that situation network congestion. In that particular situation, packets will have to queue up at these routers and wait for link queues. So you see here, wait, the key word. Delay here to transmit the packet is short, but there could potentially be wait that is a little bit uncertainly long. Okay. And hey, packets will get queued. What if there's not enough space in the queue? Packets also get dropped. So in packet switch network, we do have substantial delay. We could have substantial packet losses. One big disadvantage. Another disadvantage is here, and this one is a little bit subtle. In packet switching network, there's no circuit being established. The way we send packet is that you forward it out on the link. The next router will need to pick up everything, so you need to wait until the entire packet is received. The next router will need to receive the complete packet before the router can further forward the packet. So this is called store and forward. So the router action there passing packets is store the packet first and then forward the packet next. So this mechanism here is determining how packets are moved, okay, one hop at a time. Meaning you have one of these L divided by R every hop, every router.
Yeah, I know. For store and forward.
So
a little bit unfamiliar.
here let me illustrate the store and for effect to the end-to-end delay. So consider this scenario. The source is over here. Okay, user typing up things and generating these small packets, 1, 2, 3. One router here in the middle and receiver on the other side. And each packet here the user is generating is L bits long, and the link bandwidth is R BPS. So you see, to send this big packet over the link at this speed, this is the amount of time that's required. And a packet switch network, we need to store the packet entirely before forwarding. So entire packet needs to arrive at the router before it can be transmitted further. The end-to-end delay will be what? 1L divided by R for this hopping. Because this guy, to send it out, it requires L divided by R. This router here, receiving it, waits until O is received, and then what? Send it out again. That's another L divided by R. So if L is 7.5 megabits per second, R is 1.5. You see, each hop, 5 seconds. 2 hops, in this case, how long? 10 seconds. 3 hops, the longer, the more hops you have, the delay of sending the packets longer. This is different from circuit switch network. Bits can be streamlined. Okay, there's no need to store a bunch of bits first before forwarding it. Okay, that is saying that each bit arriving here gets out quickly, so there's no hopping. It's just the propagation delay and the transmission delay, L divided by R, from the first hop. This slide is to illustrate congestion. The scenario is A and B, 2 users generating packets, A generating A generating green packets, and B here generating blue packets. And you see these packets are generated as user A and user B are typing things up spontaneously. So green and blue, they will kind of bunch up or multiplex in a random order. Okay. Unlike in TDM, time division multiplexing, everything goes rotating, rhythmic. And this, okay, having some sort of spontaneous behavior in it is statistical multiplexing. Okay, so on packet switch network or on the data network internet, packet kind of, multiplex to each other randomly, spontaneously, depending on how they are generated. Now let me draw your attention here. The router. You see packets in case the outgoing link, bandwidth small. And incoming link here, this is 100 megabits per second Ethernet. This is only 1.5 going out. Chances very high, A and B, if both of them actively generating lots of packets, the packets will have to wait here in the queue before they get the link queues. And if there's not enough space here for the queue, the next one, the green one coming here, will need to be dropped. Well, there's no memory space to hold. And those packets waiting in the queue, it depends on how long the queue is as they comes in to the router. The queuing delay can vary. It can be a little uncertain. But transmission delay, the time it takes to go on this link is always the packet size divided by 1.5 megabits per second. And we use the full link bandwidth. So transmission delay here is very easy to get.
All right, so you get a good idea of packet switching.
Here, let me use an example to illustrate. Packet switching actually outperforms circuit switching when there are more users and each of these users are not exactly very active, sending short messages only each time. Alright, so scenario is very simple. Okay, we do have a network of end users and they're behind this router. Going out of the router is a very low bandwidth link, 1 megabits per second. And each of the users is behaving this way. When they're active, they do need a lot of bandwidth, 100 kilobits per second. But they're only 10% of the time active. In a circuit switch network, in order to satisfy these 10 users, and each at maximum requires 100 kilobits per second, so we reserve 100 kilobits per second to each of the users. And how many users we are allowed to reserve bandwidth? This is 1,000 kilobits, so we can only allow 10 users, okay, 10 circuits. But in packet switching, you see, the users are only active at 10% of time. Consider this scenario. If we have 35 users, right, the only situation that these 35 users will have trouble sending data out is when there's at least 10 users being active at the same time. So what is the probability of these 35 users and more than 10 of them being active at the same time? If you do the calculation, you'll see that it's very low. So 99.9996% of the time, in packet switch network, 35 users will do well. No trouble. So if you do have a lot more users and each of the users needs just a small portion of time to send data, which one would you pick? Circuit switching or packet switching? It's quite obvious, isn't it? And oh, by the way, anyone here knows how to derive this value? The probability of 10 of the users being active at the same time, given the active rate is 10%.
Anyone? No? Think about it. Okay, and that takes us to quiz number 3. So quiz 3 here says, we now know circuit switching, right? So we reserve a portion of the bandwidth for the data, essentially. So if I use an analogy, it's a little bit more like building a pipeline and transfer water on this dedicated pipeline. And packet switching, on the other hand, we cut data into smaller pieces, smaller packets, and then just mix them, whoever generate them, right? And the analogy will be more like, putting waters in buckets and then pass them on as where they need to go. So Q1 here is, which principle do you think the car network, the streetcars network, what kind of mechanism is running in car network? Is it more circuit switching or packet switching? And if you think now, the other transportation network that we take a lot, the train network, do you think train network is more circuit switching style or packet switching style? And Q3, which one do you like better? And this can be subjective, okay, as long as you justify the reason. Okay. Well, we don't have much time now, so my suggestion is maybe briefly talk to your teammates or talk to them and discuss after the break in case you guys need to attend the next course. So for today, there's unfortunately no in-class discussion, but we'll go through some of you guys' answer to quiz 3 from Slack workspace beginning next week. Okay, and so that's all for today. Okay. Okay, all right, guys online. I'm gonna end the stream now. Okay. So ending now.